Okay, good morning. So before I switch to the second part of the course, which is the Rupert's random walks and stuff like this, I want to come back to percolation because yesterday I feel I was a bit quick and a little bit sloppy in the statement of the convergence theorem. So I want to restate a few things that I said yesterday, just to give an introduction to why we are looking at Rupert's random walk. So recall, what we are looking at is self-percolation on the triangular lattice. And we're at the critical point, which is P equal to PC equal to 1/2. And what I told you is that if you look at the probability that given a wrong box of size n alpha by n, probability that there was a horizontal crossing of this box from the only open sides, this had a limit as n go to infinity, limit which depends only on alpha. So there is some triangular lattice somewhere. And the equivalent statement was that in a fixed rectangle, if the mesh goes to 0, the same happens, and the crossing probability converges to something. So that was a theorem that I wrote yesterday by Smirnov. I want to give you a more precise statement of this theorem, because this f is actually explicit, and if you write it in the rectangle like this, it's a hypergeometric function. You have to know these things. But there is one very nice way of stating the convergence theorem, which is the following. So take this rectangle here. So it has 4 vertices. And you know Riemann's mapping theorem, and if you don't, then you have to go to the TA session, which will be all about this. There is a conformal map mapping this rectangle to an equilateral triangle. So you take an equilateral triangle. This is supposed to be equilateral, and there exists a map phi, which is 1-to-1, which is complex differentiable, and which maps the inside of this rectangle to the inside of this triangle. And actually, if you look at the statement of the theorem, there is a 3-parameter family of such maps. So what you can do is you can fix the images of 3 boundary points. So let's say this guy will be sent, okay, which one will be correct? This one, A, will be mapped here. B will be mapped here. C will be mapped here. And once you specify the images of these 3 points, then there is uniqueness of phi. There is one invariant, which is the cross ratio between the 4 points, which is essentially a function of alpha. And so once you fix the images of these 3 points, the 4th point here, D, is mapped somewhere on the interval between A and C. So let's say somewhere here. So this is the image of D. Okay, and then if you look at the picture, there should be a crossing between this interval and this interval. So if you map the picture by the conformal map, there will be a crossing like this. Of course, if you map the discrete picture by phi with mesh delta, what you see here is not the triangular lattice. It's a deformed version of the triangular lattice. So the model here is not exactly the initial model. It's not percolation on the triangular lattice. But the topology is the same. And if you write x for this length here, and 1 for the side length of the triangle, then you can give a more explicit statement of the theorem. Actually, this limit here, f of alpha, is exactly equal to x. So this is the full statement of the convergence theorem. Not only do you converge, but the limit is explicit in the sense that if you can find phi, which is a conformal map from the rectangle to the triangle, then you can just measure x and it will give you the crossing probability. Okay, and in fact, the theorem is a little bit stronger than that. So in fact, what you can do is look at the same problem, but instead of a rectangle, you take any simply connected domain in the plane with 4 boundary points. And you look at the probability that there is a crossing between 2 boundary arcs like this, and the probability of this occurring also converges as the mesh goes to 0, and the limit is the same, in the sense that to compute the limit, you find a map phi that maps this simply connected domain to the triangle, and then you measure the length here, and it gives you the limits of this crossing probability. So this converges to x as well. And x is some complicated function of the location of these 4 points along the boundaries. This is not completely explicit, but potentially if you can figure out what phi is, then you can compute the limit. Okay, one corollary of this is that if you take 2 domains that are mapped the same way to a triangle, then the crossing probability has the same limit in both cases. And so assume that these give you the same value of x. So this is phi 1. There is phi 2 going from here to here. And they give the same x in the sense that the images of these 4 points is the same. So what you can do is you can compose phi 2 is phi 1 inverse. And if this occurs, it gives you a conformal map that maps this guy to this guy. It just goes through here. So one corollary of this particular way of stating the theorem, it's a bit backwards, but it makes more sense if you want to state something explicit first. So the corollary is the following. So if you take 2 domains and they are conformally equivalent, meaning that there is a conformal map between this one and that one which maps this vertex to this vertex, etc., then the limit of the crossing probability is the same. And the proof of the corollary is exactly this, that you map each one to the triangle, but because there is a conformal map between the two, you get the same image here. So this is the first instance of something that will come back several times in the course, which is called conformal invariance. Which I will abbreviate by CI. So it says that if 2 setups are related by a conformal map, then the scaling behavior is the same on both sides. And in fact, well, it's not difficult to convince yourself that you can prove something a little bit stronger than this particular statement. If you remember the definition of the exploration process, for something started at the boundary point and giving it curve inside the domain, then actually this also converges to some random curve in the domain. And I cannot be more precise than this before defining SLE, but let's say the relevant space is a space of curves up to reparameterization. So you want to identify curves if they are reparameterized in an increasing way. So it's something like the Hausdorff distance up to reparameterization. This is the right topology to look at. Then the discrete picture, when the mesh goes to 0, has a scaling limit here, has a scaling limit here, and these give you 2 continuous curves in 2 different domains. But what happens is that if you map the curve in this domain by the conformal map phi, which is here, what you get on the right has the same distribution as the limit on the right. So conformal invariance holds not only for the crossing probability, but also for the geometry inside the domain. So technically, this is deeper than it sounds, because going from here, from this statement to convergence of the exploration curve is not completely evident. So this refinement to convergence to the aesthetic curve, this was done by Camille and Newman. But you can go pretty far just looking at the crossing probability itself, and the argument will come back when I speak about the simple random walk and random motion. So this is the keyword. This will come back many times. And the main question, and this is where Schramm comes in the picture, the main question is, can you assume conformal invariance of a scaling limit and deduce something about the scaling limit? Can you identify the scaling limit if you only know that it's conformally invariant? And the answer is not quite, but you need a few more hypotheses. But essentially it gives you a lot of information about what can happen in the scaling limit. So this is what I wanted to restate about percolation, just as a way to introduce conformal invariance. And if you remember what I told you in the very end of the course yesterday, or Monday, I told you that the proof of this was, well, consisted in introducing some events that depended on the location of a point inside the domain, and proving that the probability of this event depended on the location of these points in some way that was behaving like a harmonic function. So there is something to say about harmonic functions, and that's what I want to start with today, after this recall about percolation. So the second discrete model I want to talk about is a simple random walk. And the relation with Brownian motion. So the goal is, in order to understand why there is conformal invariance in the limit, can you pick a simple model for which there is conformal invariance, and can you say something about why there is conformal invariance, and can you match what you need to do in this simple case and apply it to a more complicated one? So here the main theorem of this part is this, by Levy, that Brownian motion is conformally invariant. So this is a vague statement because there is again this question of reparametrization of the curve. So there will be two versions of this theorem. There will be a geometric version and there will be a process version. I will prove one of these. I will prove that the geometry of this curve, one particular aspect of this geometry, is conformally invariant. And for the full proof and the full statement up to the time parameter itself and up to the process level, you will have to go to the TA session number, I don't remember, 6 maybe? 6? 7? This? Something. Conformal invariance of Brownian motion. 4. Okay, so this week. But the weak version will be proved here today. Okay, so the first question is, if you ask an analyst about something that is conformally invariant, they will tell you that there are equations that are preserved by conformal maps, and the main one is the Laplace equation. So the fact is, if you have a domain omega and a map F mapping this to C, or to R, or to something, let's say to R, and you assume that the Laplacian of F is equal to 0. So that's the usual Laplacian, is the second derivative in X plus the second derivative in Y, or minus this if you want to be more geometer than a probabilist. It doesn't matter because it's equal to 0 anyway. So if you have a harmonic function like this, and if you take a conformal map phi mapping omega to some other domain, here you have a map to R which is exactly F composed with phi minus 1. So you first pull back here and then you apply F. Then it's an elementary computation using the Cauchy-Riemann equations. It tells you that this is also a harmonic function. We can compute the Laplacian of f composed with a conformal map. Maybe it would be nicer this way. So this is equal to 0. So as an exercise, if you want to just, it's very easy. If the Laplacian of f is not equal to 0, you can compute the Laplacian of f composed with phi. And using the Cauchy-Riemann equations, you will find that this depends on only on the Laplacian of f and the derivative of phi. But that's just an exercise. This is the fact. If f is a harmonic function, and if you compose it inside with a conformal map, you get something which is harmonic again. Okay, so what does it tell you? Well, this is one example of something you can look at, and it is not exactly the same as the proof of Smirnov's theorem, but it tastes a little bit like that. So you know the following theorem. It's not a difficult, well, the strong version is difficult, but the simple version is not too difficult. If you take a smooth, simply connected domain, omega, and assume all the regularity you want on omega, the regularity is not the thing I want to focus on, and let u be a function from the boundary of omega to r. And assume that u is continuous, assume that u is C infinity, all the regularity you want on u. And the question is, can you find a harmonic function inside omega that matches u on the boundary? And the theorem tells you that there is a unique function f from omega bar to r, such that Laplacian of f is 0 on the interior of omega, and f on the boundary is equal to u. So this is called the Dirichlet problem. And the theorem tells you that if you have enough regularity in the problem, then you have uniqueness of the solution, existence and uniqueness. So if u is here, gives you a function here with Laplacian of f equal to 0 inside the domain. So this is a very classical theorem of analysis, and it turns out that, well, if you see this theorem and if you see this fact, then you can figure out something that is conformally invariant. So you can do the following. Take two domains, omega 1 with the function u1 on the boundary. Take another domain, omega 2, with a function on the boundary, and assume that there is a conformal map between the two, or fix a conformal map between the two. Fine. It always exists by the Riemann mapping theorem, so pick one. And on the boundary of omega 2, assuming that, again, everything is smooth and everything is nice enough, and I don't want to go into the precise hypothesis you need, but let's say if this is a smooth Jordan curve and this is a smooth Jordan curve, it works. Then you can define a function on the boundary of omega 2, which is simply something like u1 composed with phi. And again, I will put phi this way. Okay, so if you have a boundary function here on the left and you have a conformal map, you can define a boundary function here on the right. Of course, if the domain is very rough, sometimes you cannot extend phi to the boundary, and then you have a problem. But assume that the domain is smooth enough that there is no problem. Okay, then what can you do? You can solve the Dirichlet problem here on the left, and you can solve the Dirichlet problem here on the right, and you get here a function f and here a function g. Is there a problem with the sound? Can you hear? Because they were, well, okay. So you can solve the problem on both sides, but because there is uniqueness here, there is one very good candidate for g, which is simply f composed with phi. If you want to define a function here given a function here, you compose with phi. And what the uniqueness tells you that G is exactly f composed with phi. So this is yet one other statement of conformal invariance. It's essentially the same, well, it looks the same as this one. You have two domains, they are related by a conformal map. You compute something on both sides, and what you get in the end is related by a conformal map. So the Dirichlet problem is conformally invariant. Okay, why do I want to tell you all about this? Because, so the point is to look at Brownian motion and to look at simple random walks. And you know that Brownian motion is strongly related to the Laplacian, because the Laplacian is the generator of the Brownian motion. So there is another thing, maybe a proposition, which is the following. Again, take a simply connected domain with a smooth boundary. Take U on the boundary and pick Z somewhere inside the domain. So from Z you can start a planar Brownian motion, a standard Brownian motion. Maybe I've used some color. So you start at Z and you launch a Brownian motion. And what you do is you run it until it touches the boundary of the domain. So you do something like this. You launch a Brownian motion until it exits the domain. So you can define tau, which is the inf of times such that B sub t, so B is the Brownian motion, such that the Brownian motion is on the boundary of omega. So this is the exit time of omega by the Brownian motion. Okay? So this is B tau. How can you try to solve the Dirichlet equation, Dirichlet problem? Well, you can look at U at the exit time. So take U of Bt, of B tau. So that's a real number. And then you take the expectation over the Brownian motion. So take the expectation starting from Z of this. So now at Z, in the exponent of E, it means that the Brownian motion starts from Z. And then it's not difficult to prove that this is a harmonic function of Z. That's essentially the same statement as saying that the Laplacian is the generator of the Brownian motion. And you can get it by saying that if you look at the infinitesimal time parameter, what you do is something that is isotropic, so you are measuring the Laplacian by the evolution of Brownian motion. Or if you prefer, you can use Ito's formula, or you can do whatever you want to get that this is a harmonic function of Z inside the domain. On the other hand, if you start very close to the boundary, then you will exit very close to your starting point because the Brownian motion will turn around its starting point many times. So if you start very close, you will exit very close to your starting point. And what it tells you is that if Z is close to the boundary, this is close to U of Z, to U of the point on the boundary that is close to Z. So in other words, this function expectation from Z of U of B tau satisfies both these conditions. It's harmonic and it extends to the boundary to be equal to U on the boundary. So this is the same as f of Z. So it solves the Dirichlet problem star, which is here. And because there is uniqueness, well, you can restate the theorem saying that the unique function satisfying these two conditions is exactly given by the expectation of U at the exit time by a Brownian motion. So this is more explicit to a probabilist. It's less explicit to an analyst because Brownian motion itself is something that is non-trivial. But at least it gives you at the same time a proof of existence and something like an explicit value for the solution. Okay, so this tells you that Brownian motion should have something to say about conformal invariance. And so I want to give you one statement that looks like this, and which is one particular version of this theorem. It's a bit weaker than what you will do in the TA session on Friday, but somehow the proof is smoother and you don't need all the artillery of Ito calculus to prove that. So look at this picture. So this is omega. Z is fixed now, and I want to define the outer perimeter of the Brownian motion. So, or the envelope of Brownian motion. So I want to define, so B sub 0t sub interval 0t is just a set of points that the Brownian motion visits. So that's a shortcut for the sets of Bt for t in the interval between 0 and tau. What I want to do is not prove that the whole curve is conformally invariant, because this is complicated. I want to simplify the question, and I want to look at the curve from the outside. So again, I will need another color. So you have this particular curve going from Z to the boundary of the domain. And if you look at the complement of this curve, it has many connected components. It has many open connected components. But only one of them touches the boundary of the domain, and the other ones are inside here. So what you do is just fill the connected components of the path that do not intersect with the boundary. And this red picture here, I want to call it B0 tau tilde. So it's the filled path of the Brownian motion. The filled path, or the envelope, or the hull, or whatever. Well, it's what you have to get if you want to look at Brownian motion from the outside. Okay, and the theorem that I want to tell you about is that B tilde, so B tilde, you can remove the dependency on the parameter from the notation because it's clear what you do. Omega is fixed, so you run Brownian motion to the boundary and then you fill the holes. So B tilde is a random compact set if omega is bounded. So I assume omega is bounded. This is a random compact set in the plane. And the statement is that B tilde is conformally invariant. And again, I will restate this explicitly. So take one domain, omega 1, take one other domain, omega 2, pick Z on the left, and fix a conformal map phi. So this time it goes to the right, from omega 1 to omega 2. So Z is mapped somewhere here. This is phi of Z. And then start Brownian motion from Z on the left, like this, until it touches here. So it makes lots of loops. And there is this set B tilde, which is here. So it's a set that is contained inside omega except for the tip here on the boundary, and it's a random compact set. So now, given this picture, you have two ways of defining a random compact set inside omega 2. So you can define K1, which is W tilde. So you launch from phi of Z a Brownian motion W until it touches the boundary. And then you fill the holes. So do the same construction in the other domain. So this is Let's say sigma is the exit time on the right. So this is a random compact set on the right. And the other compact set you can look at is just the image of this one by phi. So if this is K, you can look at K2, which is just phi of K. And the statement of conformal invariance is simply that these two random compact sets here have the same distribution. So K1 has the same distribution as K2. So this will follow from the exact computation of what the image of Brownian motion itself is by a conformal map. And the stronger statement is that if you look at the curve itself here, not only at the envelope, but all the topology inside and the order in which you visit the points and everything, then this is mapped again to Brownian motion on the right, but there is a time change depending on the derivative of phi. So this you will learn about during the TA session on Friday. And once you have this, of course, if you look at the envelope of the curve, it doesn't depend on the time parameter. So once you have the strong version of conformal invariance of Brownian motion, this is just a corollary. But what I want to do is to tell you why this is true without using Ito calculus and without using much artillery about Brownian motion. Okay, so is the statement clear? If nobody complains, I guess it is. Okay, so the argument will be, we have one thing that is conformal invariance, and that's the solution to the Dirichlet problem. So let's see if I can pretend to be Swiss. So you have the solution of the Dirichlet problem, and this is conformal invariant. The question is, what can that tell you about the shape of Brownian motion seen from the outside? So the key remark is the following. Because of the topology of the set B tilde, you are looking at the path from the outside. So if you want to prove that these two random compact sets are the same, well, it's enough to look at them from the outside. And by a monotone class result, it turns out that this is not quite dry, but it will dry, hopefully. So it's enough to show that, well, these two sets will have the same distribution if they satisfy the following thing. The distribution of a set like this is completely characterized by the probability with which it avoids some obstacle that touches the boundary. So what you want to prove is the following. I'm trying to wait for this to dry, but okay, whatever. So this is omega. This is omega 2. This is phi of z. And let's say that you pick A, and A is an obstacle. So A is an obstacle. The definition, the exact definition of an obstacle, I will say it, but I will not write it, and that's exactly what you would think as a definition. So it's something that is relatively compact inside omega, that is simply connected, whose complement is again simply connected, which does not touch the initial points. So really something that you can remove, which is smooth, and such that it makes sense to look at Brownian motion inside the complement of A. So it's just one way of modifying the domain. Okay, and it has to touch the boundary. You want the complement to be simply connected. So this is not, this would not be a correct obstacle. Okay? So K1 has the same distribution of K2. So let's say I will call calligraphic A the set of obstacles. These two sets have the same distribution if and only if for every A in the set of obstacles, the probability that K1 avoids A is the same as the probability that K2 avoids A. And that's because you are assuming that these compact sets have no holes. If you wanted to identify the whole topology of the curve, then you would need to say something about the inside of the curve, and then you would need something more than the obstacles, and then it becomes more complicated. Okay, so I will look at K1, because K1 is just a Brownian motion inside this. So what does it mean that K1 does not touch A? It means that if you launch Brownian motion inside this domain, it doesn't touch A, so it touches the boundary of omega 2 before it touches A. That's exactly the same statement. And so B exits omega 2 without touching A. So that's the same as saying that the path does not enter A before exiting the domain. And that's the same as saying that the Brownian motion inside omega 2 minus A exits in this part of the boundary and not on that part of the boundary. So it's the same as saying that B exits omega 2 minus A through boundary of omega 2 minus boundary of A. So through the open part of the boundary here. So of course, as part of the definition of the obstacles, I didn't say that A did not swallow the whole boundary, but if A does swallow the whole boundary, it's not possible that K1 is disjoint from A. So this is 0, but it still makes sense. Okay, so this is the event that you want to look at. The Brownian motion exits this domain, which is omega minus the obstacle, through one part of the boundary. Okay, what is this probability? This is the expectation starting from Z of the indicator function that B tau is in boundary of omega 2 minus boundary of A. That's just a restatement. But this is a function on the boundary of this new domain. Function which is equal to 1 here and to 0 here. That means that this probability is just the solution of the Dirichlet problem with this boundary function inside this domain. So it's the unique harmonic function inside omega 2 minus A with these boundary values. So this is for K1. If you want to compute that for K2, well, K2 will be the image of a Brownian motion on the left. So what you do is you look at omega 1, you map A back by the conformal map, you compute the exit probability on the left, and it's a solution to the same kind of equation, except here you have omega 1, and here you have the inverse image of A. But it's the unique harmonic map on the left, and then you push it back by phi. But because you know that the solution of the equation is conformally invariant, what you get on the right for K2 is the same. So what you get after going back and forth and using conformal invariance of the solution to the Dirichlet problem, what you get is that this is the same as probability that K2 intersect A is empty. So this one is relating Brownian motion to the Dirichlet problem inside omega 2. And for this one, you need to go back, so to pull A back and then solve it on the left and then push it forward. But because of conformal invariance of the solution, you get the same thing here. It's the unique function with the right boundary values. Okay, so this exactly tells you that seen from the outside, Brownian motion is conformally invariant. So this concludes the proof of this weak version of conformal invariance of Brownian motion. Okay, so that's more or less what I wanted to start with. Okay, so we have one other instance of a scaling limit. So Brownian motion is the scaling limit of simple random walk. And this scaling limit has the property of conformal invariance because it's related to the Dirichlet equation. I will start again here. So if you have questions about this, it's time to, while I'm erasing the board.
So you have proposed that the boundary function remains 0, 1 after you do the...
Well, you define it like that.
Yeah, it's
So,
defined in one case, but then you want to apply the map phi.
yes.
Does it remain 0, 1?
Well, that's the way, in the statement of the conformal invariance of the solution, you map the boundary by phi itself. So you do need phi to extend to the boundary. So that's why I'm assuming the domains are smooth, etc. But you define the new problem by mapping the initial problem itself. So there is no question of the definition of the boundary value. Okay, so we have one conformal invariant random object, and I will keep this here. But the problem is that the topology of the object is very complicated. It's very fractal. It has a boundary which has dimension 4/3, and I will come back to this. So I will just state it here. Dimension of the boundary of B tilde is equal to 4/3. But if you want to prove such a result, well, you're kind of stuck because the hull of the Brownian motion is not a simple function of the Brownian motion itself. Filling the holes is very easy to define topologically, but the boundary of the hull is visited by Brownian motion in any order. I mean, you can visit first a few points here, then here, then here. So the Brownian process is very simple, but the way it builds something inside the domain is complicated. And so there is no direct way to say much about the shape of this B tilde, except from the outside like this, but you cannot go very far if you only use this. And essentially the reason is that the Brownian motion is not a simple curve. It has lots of double points, so you can have something very complicated. So you would want something to be a simple curve. That would be easier to study, because a simple curve cannot be visited in any order. It can only be visited, well, chronologically somehow. So you would want a simple curve which is still random, and hopefully which is related to Brownian motion, and hopefully which is conformally invariant. And if you have this and it's related enough to Brownian motion, then maybe this is easier to study, and maybe you can go back then to Brownian motion and obtain information about the Brownian motion itself. So this is the goal, and at the end of the course you will know how to build such a function. But first I want to give you candidates, well, two candidates for that. So that will be part 3. So you want to define a simple continuous curve. Of course, if it has to be conformal invariant, it cannot be defined on a lattice, because the lattice will be deformed by a conformal map. And so nothing discrete can be directly conformally invariant. You need to take a scaling limit at some point. So the first thing you can try to do is to define a discrete simple curve, which is random, and show that it has a scaling limit, and that this scaling limit is conformally invariant. And this is still the first chapter about discrete models, so I will tell you about two discrete models, the LERW and the SAW. And I don't tell you right now what these mean, so of course most of you will recognize these, but especially those who have read the notes before coming. But these are essentially the two ways to construct a discrete curve that is a simple curve. So how can you provide a discrete simple curve? Well, you can start with a curve and make it simple, or you can start with a curve and condition it to be simple. And this will give rise to two different objects. It's not very intuitive that they are different, but they are actually different. Okay, I will start with this one. So this means the loop erase random walk. So you start with a random walk. Random walk is not a simple curve, but you can make it a simple curve by just removing the loops. You want it to have no loop, so you erase the loops as they are created. So, well, a lot is known about loop erase random walks, and you can define them on any graph essentially. But I want to define them inside the domain because that's the framework I'm working with. And that's exactly where you can say something about the scaling limit. So again, take omega, which is a simply connected domain. Fix delta positive. And delta will be the mesh of a discretization of omega. So you discretize it by your favorite lattice. And when you work, your favorite lattice is often a triangular one, but when you teach, it's the square one because it's easier to draw. So this is delta Z2. And you look at this intersection with omega. So this is your finite graph. It's a graph on which you will work. So pick Z somewhere inside the domain and define a simple random walk. So xn, n positive, will be a simple random walk in the plane, started from x0 equal to z. So it starts here, and you just walk to a nearest neighbor uniformly, and then you proceed. So this is a very simple object. It's very related to random motion. Okay, and you do that until the simple random walk touches the boundary. So tau here will be the inf of n such that xn is on the boundary of omega. And to make it precise, this should be omega sub delta, which is the discretization of omega. And this should be boundary of omega delta. So you wait for the walk to make its first step outside of the domain omega. And at that time, what you get is something with lots of loops, and it exits here. So this is x sub tau. So this discrete set is very close to being the same as b sub 0 tau here, except it's a discrete model. So as the mesh goes to 0, it will converge to this by Donsko's theorem. So what does it mean to remove the loops? Well, the intuition is very clear. You have a path, and what you want to do is the following. So you have this discrete path, and whenever it closes a loop here, what you do is you just erase the loop. So you erase the loop, and then you proceed. Then you walk again, and then this you erase the loop. So you are here, and then you erase this loop, and eventually you will exit the domain. And one key remark is that if you remove the loops, you will still exit the domain at the same point. So what you get is some random given this, you get this deterministic subset of the path that goes from z to this point x tau. And this is called the loop erasure of the path x. So formally, the loop erasure of x is a path defined by, it will work. So I will call it y. So to define the loop erasure of x, what you do is you start at the same point. So y0 will be x0, and this is equal to z here, but to define the loop erasure, you just look at the starting point, and you use the same starting point. And then if you follow the construction, the first step of the loop erasure of x will be, well, what you will have at the beginning is some finite sequence of loops around z. You will come back to z a few times. And every time you come back to z, you will remove this loop in the construction. And then there will be the last visit of z. And the first step after that will be kept. You will not close the loop after that. So this will be the first step of the loop erasure of the walk. So y1, so you can define this. You can define sigma 0, which is the maximum of the set of n such that xn is equal to x0. So this is the last visit of the starting point. And you define y1. So the first step of the loop erased walk is simply x at times sigma 0 plus 1. So you wait for the last visit, and then you look at the next step. Then you define sigma 1, which is the last visit of this guy, because what you have, once you have this walk here, you will make loops around it, which will be removed from the picture. And then after the last visit, you have the next step. And the next step will be kept in the construction. So sigma 1 is the last visit. So the max of n such that xn is equal to y1. And here you define y2, which is x at times sigma 1 plus 1. I forgot to use the other side of this business. That's why it's still wet. I'm sorry. Okay, so this is sigma 1, and then you proceed like that. Sigma k will be the last visit of the point yk. And yk plus 1 is simply x at times sigma k plus 1. And so you can do that until you exit the domain. And what you get is that there will be some k0 at which the construction stops. So this stops at some k0 such that x sub sigma k0 is x tau. So in other words, one of these times will it be exactly the exit time. Sigma k0 will be exactly tau. And then you stop. So you have this finite walk, and you will remove all the loops, and you get a simple walk that goes from z to the boundary. So this is defined in a very general setup. You can start from any discrete path and erase the loops like that. And you get the loop erasure of x. And the definition is that the loop erased random walk is the loop erasure of x if x is a simple random walk. So that's a natural definition. You want to construct something that is random, that is simple enough, and that has no loops. So you start with the simplest random curve, which is a simple random walk, and you remove the loops. Okay, so what can you do with this object? You can try to see if there is a scaling limit. That's the whole goal of the course, is to look at scaling limits of discrete models. So what you do is you look at that. There is this mesh delta, which is positive, and you let delta go to 0. So you can look at loop erased random walk from A in delta Z2 intersection with omega. And the question is, what happens when delta goes to 0? So as delta goes to 0, what happens? So the first conjecture would be the simple random walk itself converges to Brownian motion. If you erase the loops, that's a topological operation. It doesn't depend on the parameterization. It doesn't depend really on the way you define it in the discrete level, as soon as it's chronological. So the natural conjecture would be that this converges to somehow the loop erasure of B between 0 and tau. So the loop erasure of Brennan motion. You would hope that erasing the loops and taking a scaling limit converges. That a discrete loop will correspond to a continuous loop, and that you can do that. You can compute, you can define the loop erasure of Brennan motion and then erase, and then prove this convergence, essentially as a corollary of the Donsker theorem. Okay, that's a natural conjecture. So that's a conjecture. But as soon as you try to prove this, you think a little bit and you realize that this conjecture makes no sense at all. So this makes no sense. And the reason is that the loop erasure of Brennan motion makes no sense. So why is that? That's because Brennan motion is more complicated than you might think. There is a last visit of the starting point of Brennan motion, but this is 0. You don't come back to a simple point. There is a last visit of any point on the path, but then looking at last visit plus 1 does not make sense. And so what you might want to do is to look at loops that are above some level and erase them. So you look at the first loop of diameter more than epsilon. This you can do. You can remove this and then you iterate. And in the end, you get a path which has no loop of diameter more than epsilon. And then you hope that as epsilon goes to 0, you get some monotonicity telling you that you remove more and more loops. But the problem is if you start to remove a smaller loop, so the path might do something like this, and epsilon is something like that. So if you remove the loops that are larger than epsilon, you will remove this, and the loop erasure will be something like this. If I'm not completely wrong. So this is the first loop, so you erase it and then you continue. And if you remove the loops that are smaller than, say, epsilon prime, which is smaller than this guy, well, you remove this, but then this is not a loop anymore. So if you remove smaller loops, what you get is this. And that's very different. And this will occur at any scale, so there is no way to prove that as epsilon goes to 0, the epsilon loop erasure of Brennan motion will converge to anything nice. And in fact, well, you can come up with several definitions that will give you continuous curve which are simple, but none of them is simple enough that you can relate the construction to that of the loop erased random walk. So it makes no sense, and the question remains that there should be some scaling limit, but it's very difficult to describe using objects that you know, using classical objects. So nevertheless, there is still this link with simple random walk that I mentioned, which is that the exit distribution of the domain by the loop erased random walk is the same as the exit by a simple random walk. So this is discrete harmonic measure, if you know what that is. So it's strongly related to the Dirichlet problem, and this was conformally invariant. So you expect some conformal invariance in the limit. So at least the exit point is conformally invariant. This we know from the previous theorem about conformal invariance of Brennan motion. If you define loop erased random walks in two different domains and look at the exit distributions, they are conjugated by the conformal map between the domains. So this we know, it's not part of the conjecture, it's a corollary of the previous theorem. And so you would expect that the geometry itself is conformally invariant. And I will not have time to prove that in the course, but it is the case. And the limit, the scaling limit, is one of these conformally invariant curves that were introduced by Schramm. In fact, historically, that's the discrete model he was looking at when he introduced SLE. And the theorem is that the loop erased random walk with mesh delta converges to SLE2, which is conformally invariant. So again, I'm being very sloppy about the statement of this theorem. It's the same sloppiness as on Monday about convergence of the exploration of percolation to SLE6. So that's kind of intentional to be sloppy at this point, because I don't want to go into the definition, the precise definition of SLE right now. I will define it on Friday. But once you know what SLE is, you can come back to the statement of the theorem and it will make sense. So just a remark. This is convergence in distribution, and the topology is a topology on curves up to parameterization. I mentioned it a few minutes ago, that you can define if gamma 1 and gamma 2 are curves in omega. So this is defined up to time tau 1, this is defined up to time tau 2. There are two curves in omega, and you want to say how close they are in order to define convergence in distribution. So it turns out that the right definition of a distance between gamma 1 and gamma 2 is a distance up to time parameterization. Well, it makes sense if you look at compact sets, and it makes sense if you look at this definition, because the time parameter of the loop erased random walk is something complicated. This is not a stopping time, so you can guess that studying the parameterization of the walk will be something tricky. So you want to forget the time parameter as soon as possible. So you want to look at the inf over all functions phi going from 0 tau 1 to 0 tau 2. So this is a change of parameter going from this time interval to this time interval. So that maps gamma 2 into a function defined on 0 tau 1. And so you have, sorry? It's, yes. It should be strictly increasing. Then you have two natural curves. You have gamma 1 with its initial parameterization, and you have gamma 2 composed with phi, which is a reparameterization of gamma 2. And these are defined on the same time interval. And then what you can do is to look at the difference, and you look at the L infinity norm. So look at this supremum, and you minimize it over all possible reparameterizations of the curve. So this is, well, it's the same as in the Gromov-Hausdorff case. It's not exactly a distance, because it can be 0 for different curves. It will be 0 if gamma 1 and gamma 2 are curves which are one time change of one another. So you will want to identify curves that are that give you distance 0, so curves for which there is a time change mapping one to the other. But once you have identified this, in the quotient space, this is a nice distance. And it's for this distance that this is convergence in distribution. Okay, just one remark, and then I will switch to for the rest of the course. What does it mean that distance is 0? It tells you more than just saying that the compact set is the same. Here I'm not assuming that the curve is a Jordan curve. So you can look at this curve and that curve. So let's suppose the paths of these curves are very close. because one is in the tube around the other one. So in terms of the Hausdorff distance, they are very close. But in terms of this, they are not very close because you cannot parameterize the white curve in such a way that it goes forward all the time. At some point, the white one will have to backtrack and the yellow one will have to proceed. So the distance between these two is the same order as the length of this folding of the curve. Yeah? Sorry? Here? Okay, this is sloppy, but any lattice for which simple random walk converges to Brownian motion, you have this. Let's say periodic. The initial proof was done in Z2. There is more trickiness involved if you want to do it in a general lattice. But it's not deep trickiness. It's technical trickiness. So these curves are close in the Hausdorff sense, but they are far away in this sense. So this is finer than the usual Hausdorff distance. Okay. So this is a statement. It's a bit less sloppy than yesterday because at least I told you what topology was involved. But I still haven't told you what SLE is, and you will have to wait a little bit because, well, then there is some machinery about love in the chains, which I will introduce tomorrow. Okay, so there's two things I still want to say today. I want to tell you a few words about the self-avoiding walk, and I want to tell you something about the domain Markov property. So this time I will try to do it right. So we would like to identify the possible scaling limits. So here I'm following the paper by Schramm. You would like to identify the possible scaling limits of loop erased random walks or similar objects. So you want to accumulate as many properties of the scaling limit as possible. And if possible, you want to get enough information about the possible limits to identify it possibly up to a parameter. Typically, you have convergence of the simple random walk to Brownian motion, but there is one parameter which is the variance of the Brownian motion that you get. And this cannot come from just abstract nonsense. It will come from computation. So here, what you will end up with is very similar. There is reasoning telling you that if you have a certain number of properties, then the scaling limit has to be in a one-parameter family of random processes. But figuring out the value of this parameter is something non-trivial, and it will need more work than just obtaining the existence of this one-parameter family. So what do we know about the scaling limit if it exists? Well, we can guess that it's supported on simple curves. And why is that? Because if you want the loop erased random walk to create something that's in the scaling limit will create a loop, it means that the simple random walk behind it needs to make something very unlikely. If you want the loop erased random walk to almost make a loop, it means that, so if the loop erased random walk has to do this, the underlying simple random walk needs to, well, doing this is free because you erase the loops, but then you have all sorts of loops that you have erased around the loop erased random walk. But these all need to avoid your past here. This is forbidden because this would be erased by the construction. So if you are very careful, you can compute the probability that this occurs, that you create a fjord like this, and prove that this actually is very difficult, so that you get an a priori estimate telling you that whatever the scaling limit is, if it exists, it has no loop. And you don't make discrete fjords like this that would create the loop in the scaling limit. So if you start accumulating features of the scaling limit, what you get is that it has to be a simple curve. It has to be related to conformally invariance. because the simple walk is, because there is this business of exiting distribution. So you expect some conformal invariance. But this is not enough. So what you need is something that I will just introduce right now, which is the domain Markov property. Markov property. So when you want to identify the scaling limit of simple random walk, the Markov property of the walk is very essential. And here you would need something similar to say that essentially the geometry of the curve given one half of the curve depends on the geometry of this half in a very, well, in a not too wild fashion. So I give you the proposition, which is that loop erase random walk has, so this is the discrete model, the loop erase discrete random walk, has the domain Markov property. What does that mean? Well, it means, well, formally, it's this with a left pointing arrow, so it's loop erase read backwards has the domain Markov property. What it means is the following. So take domain, take Z, take a loop erase random walk in this domain, like this. Look at the last point. So the last time of the random walk, I called it K0. So this is a random walk, and this is Y sub K0. What you can do is you can condition the loop erase random walk to end by K0. It's just the same as conditioning the simple random walk to exit at K0. So if K0 is accessible as an exit time, as an exit point, you can do it. So the loop erase random walk seen backward is just starting here. And it has the domain Markov property. That's exactly what you expect seeing the name, that if you condition this to have a certain beginning, then what you see for the rest of the curve is the same as the loop erase random walk in the new domain. That's the most natural thing you can do. So the law of Y, given that yk0 is little y0, yk0 minus 1 is little y1, up to yk0 minus something, 12, equals y12. Of course, this is true for any fixed value of 12. If you condition the end, if you condition the walk by the last 12 steps, assuming this is not written, but assuming that this is a possible end of the walk, so you fix 12 possible exit steps of the walk. So like this. So this is y0, and this is y12, and this is a finite path of 12 steps. Well, this is the same as the law of a loop erase random walk. So you know the distribution of these first steps. So the information you need is about the beginning of the walk. So between 0 and k minus 12. So between 0 and k0 minus 12. The law of this segment of the walk, given the future, is the same as the loop erase random walk in the domain which is omega minus this, so minus y0, y12, condition that you exit at little y12. So let me restate that. If you take a loop erase random walk condition to exit here, and you somehow know the information about the last 12 steps, the way it has to reach here to end by these 12 steps is exactly the loop horizontal walk in the complement of this, ending at the tip. So that's a Markov property. It tells you that if you know the beginning of the reverse loop horizontal walk, the rest has the same distribution as what you started from. Except, well, of course, it's not the same because it doesn't live in the same domain. But this is the natural domain at which you have to look, and what you see is exactly the loop horizontal walk. Okay, so the proof of that, I will leave it as an exercise. It's not very difficult. And the key ingredient to prove this is the following. Turns out that there is an explicit formula that tells you the probability that the loop erasure of x is a given path. So the probability that y is, so this is little y, but I want something else. So z0, z1 up to zk0. The probability that the loop erased one walk follows exactly this path. What is it? It's the sum over all x. So the sum over all possible simple random walks such that the loop erasure of x is y. Of the probability of seeing exactly this random walk, which is 4 to the minus the length of x. So that's not very explicit. It's just saying that probability that the loop erased random walk is something is the probability that whatever you started from has a loop erasure that is this something. But then if you look at the construction, what you have is first a family of loops around z0, then a step, then a family of loops that avoid z0, then a step, etc. So if you sum over all possible walks, you can adapt this sum according to this decomposition of the path. So for that I need a definition. So the green function, it's not exactly the same as the green function, but it's similar. At a point z in a domain omega is the expected number of returns to z starting from z before exiting omega. So omega is the domain. You start at z. You count how many times you return at z before you exit omega. So this is finite because omega is finite. It's bounded from the beginning. And what you get when you do this sum, well, first you will have a certain family of loops around z0. And if you sum over all the ways to do loops like that, you find exactly this. So you find g of z0 in omega. Then you need one step going from z0 to z1. So this costs 1/4. Then you need to make loops around z1 that avoid both the boundary and z0. So if you sum, you find g of z1 in the domain which is omega minus z0. Then 1/4, etc. And then each term is something like 1/4, and then there is this green function of zk in the domain omega minus z0 up to zk minus 1. And you go all the way, and the last one is a 1/4, which corresponds to the last step. So once you have this formula, you get 1/4 to the length, and this will be very adapted to this. It will come in the conditioning. There will be a 4 to the 12 here that is not here, but it's in the conditioning. And there will be this product of green functions. But then you have green functions, so you are very happy. And the second argument is something like this. Green function of z in omega times the green function of z prime in omega minus z. This is the same as green function as z prime in omega times the green function at z in omega minus z prime. So this is kind of a commutation relation between the green functions. And it tells you that, well, the way you can see this is if you look at the path from z to z prime, it has to do a few loops at z and then go to z prime and then loops at z prime without coming back to z, which is this. But you can see it backwards, and if you see it backwards, it does loops at z prime and then goes to z and then makes loops at z without coming back to z prime, which is this. But because the work itself is time reversible, what you get is the same sum, so you get the same contributions in both cases. So this is definition of the green function. This is easy from path manipulations. And once you have this, well, what you can do is instead of making the products from the start, you can make the products from the end. And you apply that recursively, and you collect everything that is about the last 12 steps. And it comes in the conditioning. And in the end, you get exactly this for any path between z0 and y12. The probability is the same here and here. So you need to implement this computation, but once you have these two arguments, it's not difficult to put the pieces together. So I leave this again as an exercise. It's a little bit more serious than the previous exercises. It's not very difficult. So you just take these two ingredients and then you shuffle them. And if you shake strong enough, you get this. And if you don't, you get stuck, but you won't get anything wrong anyway. Okay, so I still have maybe 5 minutes. The time master has vanished, but I want to say a few words about the self-avoiding work. But it's not wise to say many things about the self-avoiding work, especially in 2 dimensions, because essentially nothing is known in 2 dimensions. Of course, in high dimensions, a lot is known, and there are specialists in the room about the high dimensional case. But in 2 dimensions, we have conjectures, but we have no tool. So there is nothing we can prove. So remember what we wanted to obtain, what we were looking for was a simple curve that was random and that possibly had to do with conformally invariant. So the definition of the loop theory as random walk is very easy. It makes sense. But it's not clear why it's, well, it's not the first definition that comes to mind if you want to define a discrete simple walk. What you can do is you just take a simple random walk, but you condition it to be self-avoiding, to be simple. So I will just do pictures because in 5 minutes there is nothing I can really define. But, well, there will be one picture and one formula. So what do you want to define? You want to define a law on simple walks in a domain. And I want to make this picture because the topology will be different, and this other topology will come back when I speak about SLE. So from now on, all we saw today was one domain, one point inside the domain, and some curve going from this point to the boundary. Well, it turns out that if you want to look at self-avoiding walks, this is not the easiest case you can look at. What you can do is change the topology. You look at the domain, but instead of going from one point inside to one point to the boundary, you can look at walks connecting two points on the boundary. So take a domain, like this, and take 2 points A and B on the boundary. So of course, this is still a discrete domain. And then you want to look at simple walks between A and B. So pictures like this. So how can you define that? Well, you can look at the set of self-avoiding walks between A and B. And because omega is bounded, this is a finite set. So you want to know on this finite set. So the first one that comes to mind is the uniform distribution, but you might, well, if you're a physicist, this is not completely natural. What you want is to add some fugacity per bond, or something like that. So pick x, which is positive, and you define mu x, which is a measure on the self-avoiding path between A and B, defined by mu x of the walk omega is exactly x to the length of omega. So you should think that if x is very small, you force the walk to be very short, and if x is very large, you force it to be longer than it should. And so, well, said like that, you would expect a phase transition, and there is x critical, which is the same as 1 over the limit of the number of self-avoiding walks of length n to the power 1 over n. So it's the inverse of the connectivity constant of the lattice, such that the following happens. If x is less than x critical, then what you get is trivial. You go from A to B in a straight line, as short as possible, and the scaling limit is just a green line. So the model becomes deterministic. If x is bigger than x critical, so you want the walk to be longer, and the walk converges to a space filling curve inside the domain from A to B. So it's really densely packed, and it turns out that this is SLE 8, but this is what you get if x is too large. But if x is equal to x critical, so somehow at the point where x is well adapted to the problem, then the conjecture is that you get something non-trivial in the limit. And so the conjecture is that you get something conformally invariant, which turns out to be SLE for parameter 8/3. Okay, so that's a definition. That's another definition of a simple path. The topology is different, but you might try to define this from Z to a point on the boundary and see if it is related to loop erase random walk. So a first hint that they are different is that 8/3 is different from 2 over there. But already at the discrete level, they are very different processes. Okay, so this was just for definition. I might come back to that when I speak about the restriction property at the end of the course. So keep that in the corner of your mind, but I just wanted to show you this picture because it fits there in the framework of the course. Okay, so that's about it for today. Tomorrow I will start with more geometry and more deterministic stuff about Lovener chains. And then I will introduce SLE on Friday. Okay, thank you. Any questions? No? Okay, so I guess there's a coffee break now.